Hello there and welcome. This video is on section 4.6, finding intervals on which a function is increasing and decreasing, and also concave up and concave down. If you've been watching the videos and you've watched the video on 4.1, most of this is just a repeat of that content. There's nothing really new. Maybe it's just organized a little bit different way. But I had to talk about increasing, decreasing, concave up, concave down in order to help sort of motivate the ideas and the concepts behind, local minimums, local maximums, inflection points, critical points, things like that. So let's say let's do three problems, practicing increasing, decreasing, concave up and concave down, and that'll be today's video. Okay, so just a recall of what we mean by increasing, decreasing. Increasing, of course, means going up, but mathematically, the definition of increasing is the derivative is positive, right? So if you have the derivative at any particular point is greater than zero, then we say that this function is increasing at that location of a. And if the derivative is less than zero, then it's decreasing. And we're looking for segments. We're looking for intervals in which all of the derivatives are positive or all the derivatives are negative. And a very important thing is that because we're looking for switching between positives and negatives, it's only possible for a function to switch between increasing and decreasing at a critical point. If you don't remember what a critical point is, that is just where the derivative is zero or the derivative is undefined. And I'll show you examples of those in a moment. Likewise, for concave up, concave down, the definition is very, very similar, except it uses the second derivative. So if the second derivative is greater than zero, it has bowing up concavity. So we call this concave up at that particular point. And if the second derivative is less than zero, we call that concave down. And again, we want to find out intervals, sections in which it's concave up and sections where it's concave down. And so we're looking for when it switches between concave up and concave down. And then we have this very important thing right here. A function can only switch between concave up and concave down at an inflection point. Inflection points could be a critical point, but it also could be when the second derivative is equal to zero or when the second derivative is undefined. So we're really going to be doing the process of finding the first derivative and when it's equal to zero or undefined. And we're going to do the same thing with the second derivative. We're going to take the second derivative, that's d squared y dx squared, and we're going to find out when that's equal to zero or when it's undefined. And then we'll be able to quickly figure out which intervals are increasing, decreasing, and concave up, concave down. All right, let's show you an example of just what I'm talking about. All right, so my first function here, that's a function I've used several times before. This x cubed minus 9x squared minus 21x plus 5. It's a nice function to illustrate things. We're trying to find where the function is increasing, decreasing, where it's concave up, concave down, just like we mentioned in the intro. Okay, so we're going to find some critical points. Critical points are when the derivative is equal to zero and the derivative is undefined. So I got to find the derivative. I'll be differentiating this thing using our standard shortcut rules. And then we have to set it equal to zero. And we also have to find out when it's undefined. Oops. Okay, so this is a x squared type of equation. It's a parabola type thing. There are different ways of solving x squared type of equations. I've made this one factorable. The easiest way is to use the quadratic formula unless you're very good at factoring and the problem was set up ahead of time to be factored. If you just pick random numbers, it's not going to be factorable. The person who made the problem has to set it up so it's factoring. So please don't make the assumption that all these things are factorable. That is something that many students come from pre-calculus with a misunderstanding. I just set this up to be factorable, but in general, one would just use the quadratic formula. That's what it's there for. So I'll factor this by taking a 3 out first. It's a common term. And then I'll do the sort of pairwise factoring. You have different methods of factoring, which is great. I'm not going to show like 4 different methods of factoring, but you really should verify that your factoring is correct. When you have a bunch of things multiplied equals 0, then we know one of them is 0. I know 3 can't be 0, so that's not a interesting situation. But x minus 7 equaling 0, that happens when x equals 7. I guess I'll put an X to this so no one gets confused. That's not possible. So we don't get a critical point from that situation, but we do get one from x minus 7 is equal to 0, and we do get one from x plus 1 is equal to 0. And so we definitely have two critical points, 7 and -1. Okay, is it undefined? Well, this is a parabola. Undefined would be something like division by 0 or square root of a negative number or the log of a negative or 0 or tangent of pi over 2. There's a very short list of things which are not computable in mathematics. Division by 0 is by far the most popular. We don't have any division in this problem, let alone division by 0. We have no square roots. We have no logs. We have no tangents. It's never undefined. It's a parabola. It's never undefined. So we have two critical points at x equals 7 and x equals -1. And then we're going to find additional inflection points. The reason why I say additional, just to remind you, is that x equals 7 and x equals -1, one of those could be an inflection point, or both of them could be inflection points. There's no guarantee what those are, but they're critical values. We need to find possible additional inflection points by using the second derivative. So maybe none of these are inflection points, maybe one or two, but we need to search for all the possible inflection points by finding when the second derivative is equal to 0. So I'm just going to take this first derivative equation and I'm going to differentiate it. So the derivative of 3x squared is 6x. Derivative of minus 18x is minus 18. And that's our second derivative. We need to take our second derivative, set it equal to 0. And we need to find out when the second derivative is undefined. And this is a linear equation, so you know that lines are never undefined. So this is never undefined. We'll have some that are undefined, but this first one, no undefined values because you can't divide by 0, etc. If I solve this equation, this linear equation, I get x equals 3. So x equals 3 is an additional inflection point. It may be the only inflection point, but it's definitely an inflection point. All right, so now we know that between the critical points, the function can switch between increasing and decreasing, and between inflection points, they can switch between concave up and concave down. Now, at this point, it's your choice. You can classify these as inflection points or maximums or minimums. Some people like doing that, some people don't. I'll show you your technique, whichever you choose. If you want to classify them, we're going to classify them as a local max, a local min, or an inflection point. So those are our choices of what those could be. And the second derivative test is what we oftentimes use. It's very quick. We already have the second derivative. So we take the second derivative and you put in the critical point. So you take the number 7 and you put it into the equation. And you do the same thing with -1. You're going to take the second derivative and you're going to evaluate it at that critical point. And depending on what you get, you can know whether it's a max or a min, or you have to do further investigation. If I plug in 7, I'll get 6 times 7 minus 18. Which is 42 minus 18. I'm not so good with arithmetic, unfortunately, and I don't care. It is greater than 0. 42 minus 18 is a positive number. If it is positive, the second derivative is positive, that means it's concave up. So the thing at the bottom is a minimum. So x equals 7 is a minimum, a local minimum. And then plug in -1, we get 6 times -1. You know, I'm using this formula, 6x minus 18, right? 6 times -1 minus 18, that's -6 minus 18. -6 minus 18 is more negative, so this is less than 0, which means it's concave down. And it's this concave down thing, what we call the top here, is called a local maximum. So we have let me clean this up a little bit so it's easier for folks to read. We have this one right here is a local Let's see, it was concave up. So this is a local minimum. And this one here was the local maximum. All right. And then we have one inflection point. So we have two possible places for it to switch between increase and decreasing. That's 7 and -1. And then we have one possible place for it to switch for concave up, concave down. That's 3. All right. So how do we do this? Well, the method that's deemed to be easiest is just to use some test points. So I'll show you for concave up, concave down. I mean, for increase and decreasing first. So increasing, decreasing. We know it has to switch at a critical point. We know that -1 and 7 are critical points. And we're going to be using the derivative to see if it's increasing and decreasing in the intervals in between. So these are x values, and then we're going to put it into the derivative equation because we're interested in knowing increasing, decreasing. Increasing, decreasing by definition is when the first derivative is positive or negative. All right, so what is my first derivative equation? It's the one over on the left, 3x squared minus 18x minus 21. And I need to plug in some numbers that are in the regions not at the critical points, but before and after the critical points. So I need to plug in at least 3 numbers. One number below -1, for example, like -2. Some number between -1 and 7. It could be any number between -1 and 7. I'll choose 0, and a number bigger than 7, like 8. Or you could choose 10 or something like that. And then you just plug it into the equation. Here's your equation. You plug it into the equation. Now, I'm not going to do these by hand, partially because I'm not good at doing it by hand, and also I'm a little bit lazy. So I have prepared Desmos here. This is our function, y equals x cubed minus 9x squared minus 21x plus 5. It looks like this. Of course, we don't want to rely on a graph. The purpose of us doing calculus here is so that we don't get fooled. We know for sure where the critical points were, where the inflection points are, where it's increasing, decreasing. We don't have to rely on a graph. And I'm sure most of you are very, very smart and you can zoom around and say, oh, okay, look, there's a part over here. I didn't see it first. But remember, the idea here is we're not relying on a graph, right? We need to know, does it turn some more? If I zoom it out again, does it turn again? It certainly doesn't appear that, but we could be easily deceived. So we definitely want to know more than just what a picture will tell us. So what I've done here is I've written the derivative equation, that's 3x squared minus 18x minus 21, right below. So that's the derivative equation. I don't really want a graph of it, but that's the derivative equation. What I want is a table of it. So I'm going to change this thing into a table. And then I'm going to plug in my values. So remember, my values were -2, 0, and 8. I'll plug in the -1 and 7 just for fun. So there's -2, -1, 0, 1, and I think 8. So most of the numbers actually came up just by default. Let me double check. -2, -1, 0, 7, and 8. Okay, so let me change this to 7 and 8. Okay, so -1 and 7 were the two critical points. I'll flip back real quick for you to remind you. -1 and 7 were the two places where the derivative was equal to 0, which is where we had a critical point. And in fact, that's confirmed in our little table. -1 has the derivative equal to 0, and 7 has the derivative equal to 0. So what happens on the side, the left side of -1? The derivative is positive. In between -1 and 7, the derivative is negative, and after 7, the derivative is positive. Remember, this is the derivative equation right here. This is not the original function. So using Desmos, I got 27, 0, -21, 0, and 27. Okay, I forgot them already. These are zeros. Sorry. 27 and -21. Okay. 27, -21, and 27. All right. So since the derivative is positive here, this is an increasing section, and all the numbers in that section are increasing. I know that because the only place it could possibly switch from increasing or decreasing is at a critical point. And here's our first critical point right here. So it could switch at -1, but it can't switch anywhere else, right? Before -1, it can't switch at -3 or -8 or -10 or -1,000,000, because we would have found a critical point where it could switch at. We didn't find any of those, so we know it never switches again, except at -1 and 7 potentially. Negative 21 means the derivative is negative. That's called decreasing. And here's the switching point. There's a critical point. And 27 is positive. So this is increasing, increasing. So we have intervals. We have the interval from negative infinity all the way up to -1. That is increasing, right? That's the interval all the way up to -1. Let me make sure that looks like a -1, kind of looks like a 4. Okay, -1. So that's increasing section. Then we have from -1 to 7. That was a decreasing section where the derivative was negative. And then from 7 and beyond, so I'll just write it up here, from 7 and beyond, we have also increasing. So we have 2 increasing sections and a decreasing section. And we can certainly verify that on our picture. Here, below this critical point at -1, it's always increasing, 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 increasing. It gets to -1, which is up here somewhere, and then it starts decreasing, decreasing, decreasing until it gets to the next critical point, and then it's increasing, increasing, increasing. So that's the gist of all the intervals that are increasing, decreasing. And we're gonna do the same thing for concave up, concave down. So we'll just do our x values, and we will do our second derivative because that tells us concave up, concave down. So our second derivative is 6x minus 18. We only have one inflection point, 3. So we need to find out what's happening before and after 3. So like at 2 or 1 or 0 and 4, something like that. And that's for the second derivative equation. So I'll take my second derivative equation and I'll plug in some numbers. And I made some space for that here in Desmos. So here's my second derivative equation, 6x minus 18. I'll just turn on the little table here. And let's see, we have the numbers. What did I choose? 0, 3, 4. So I can get rid of these guys. 0 and 3 and 4. So we have -18, 0, and 8. And again, it makes sense that you have 0 here because that's how we found 3. Remember, the way we located x equals 3 was we took the second derivative and set it equal to 0. That was this whole thing right here. Take the second derivative, set it equal to 0. That's how we got 3. So yes, it totally makes sense when I plug 3 into the second derivative equation, you're going to get 0. All right, so what happens to the left of this thing? It's negative, so we call this concave down. And over here it's positive, so it's concave up. So it definitely switches. This is an inflection point. It switches at this inflection point from concave down to concave up, and it never switches again. How do I know this? Because I would have found more inflection points if it switched again. It can only switch at an inflection point. So, there you go. And so now we know that the intervals from -infinity all the way to 3 for my x's. Oops, I'm using interval notation like this. -infinity all the way up to 3. We have concave down. And of course, in the other interval, we have concave up. Okay, so I will show you the way to do this very briefly. If you didn't want to classify, some people don't bother classifying whether they're local max or local min. And so it's a little bit different, but it's basically the same thing. Okay, so just to aside on WebAssign, when you're entering your answers, the author of WebAssign is a mathematician, and mathematicians oftentimes don't they don't use interval notation like I do. I like this kind of notation, 3 less than x less than infinity, because I can see it's between 3 and infinity. What they oftentimes will do is they'll do 3 comma infinity, as the interval notation. So just be aware that when you enter it into WebAssign, they typically ask you to enter it as interval notation. So it looked like 3 comma infinity. So you can let me know if you're not familiar with interval notation. We have done it several times before, so I can help you if you're a little bit rusty on that. All right, and then of course, really briefly, as I mentioned, how do we do this if we don't bother classifying them? Classifying them was an option. And so if you don't classify them, then we don't really know if 7 and -1 are max and min or inflection points. Specifically, they could be inflection points. So these could be inflection points if we don't classify them. So when we do our second derivative thing, our second derivative equation was 6x minus 18. We definitely have the number 3 that we're going to test because, or test on the right side and left side of 3, because we need to know whether it's concave up or concave down around 3. But -1 could also be an inflection point, and 7 could also be an inflection point. So you'll just have to use more data in the second derivative. Let me make this just a little easier to see because I don't want to make it so smushed in. So we got -1, -1, 3, and 7. Since we have 3 potential inflection points, there are 3 places it could possibly switch from concave up to concave down. Once again, we're going to test something over here, test something over here. Oh, below -1 is like -2. 0 is in between, and let's say 4 is in between, and 8 is over here. So we're going to test more numbers because we don't really know for sure whether -1 and 7 are inflection points, because this particular method, you don't really bother classifying them. So I have more numbers to plug into the second derivative. So -2, -1, 0, 3, 4, 7, 8. Let's see if I can remember some of those numbers. So here's my second derivative thing. I need -2, -1, 0. Now I'm losing track a little bit. I gotta look it up. Sorry. -2, -1, 0, and then 3, 4, 7, 8. Okay. Don't yell at the screen at me. I can't hear you anyway. Okay. So now we know at -2, the second derivative is negative, so it's concave down. It's still concave down. It's still concave down. It's just down, 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 down. Here is where it could switch because that's where it's 0. And yes, it switches. So here we have all the way until 3, we have a negative second derivative. So it's concave down, it doesn't switch. It's always concave down to the left of -3 and to the left of 3. And to the right of 3, it's positive, positive, positive. It never switches. So it could have, but in this case, it didn't. So we know that all the numbers here are negative to the left of 3, and all the numbers are positive to the right of 3. And those numbers, of course, are second derivatives. So this is a positive, 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 and this is where it was 0, and this is negative, negative, negative. So we know in this particular region, it's all concave up, concave up. And in this region here, it's all concave down, and 3 is where it switches. And we'll get the exact same answer, right? With the concave up section would be -infinity to x to 3. That's where it's concave up. And the concave down section would be the next part from 3 to infinity. And that would be the same as what we found before. And you can also verify this on the picture. So concave up, that's this section right here. Oh, did I get it backwards? Concave up, concave down. Yeah, I got it backwards, right? So let me see what I did wrong. Oh, it's negatives, negative, negative, positive. Don't yell at me. Okay, I'll get it right. Negative, 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 positive, positive, positive. So I just wrote them backwards. Okay, that tells you how good my short-term memory is. All right. Well, I know the math, I just can't remember anything. So this was negative, 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 0, positive, positive, positive. Sorry. Sorry. So this is negative means concave down. So it's concave down this section, and positive means concave up. So it's concave up in this section. Let me actually see if it's the same answer as before, please. What did I have before? I had -infinity to 3. It's concave down, which is what I have again. Okay, so I now it matches up, and it should match the picture too. This is down. So here's the picture. Yeah, here it's concave down. It has this kind of shape all the way to the left. It doesn't switch until somewhere right around here. I don't know if you can, I guess it's at 3, right? So if you can imagine like it has this kind of shape to the left of 3 and this sort of shape to the right at 3. And 3 is exactly where it switches. This 3 is where it switches from being concave down to concave up. Somewhere right around there. I can't hit it exactly with Desmos. All right, so there's a full worked out problem with concave up, concave down, and of course increasing and decreasing. And that's what this section's about. So there's nothing else for me to demo here, except we'll do a couple more example problems. But that's the strategy. That's the strategy on all of these concave up, concave down, increase and decreasing. Find the critical points, find the inflection points, any additional inflection points, make a list where its derivative is positive, where its derivative is negative, make a list where its second derivative is positive, when its second derivative is negative, and then you can write down the intervals for your answer. All right, it's definitely not a quick problem, but it is rather straightforward once you know what to do. All right, so let's go on to the next page where I have a couple more examples. And of course, I will again mention that you're free to stop the video at any time and give these a try. So I have a couple different functions here, B and C. Perhaps you want to try, see if you know the steps or can review the steps and figure it out. Sometimes it's really good to do that so you know which parts you really got and which parts you're a little bit rusty on and need a little bit of help. And then I'll go through my solution and show you, well, where you might get going if you got stuck somewhere. So I'm going to pause the video, write out my solutions, and then hopefully you'll write out your solutions. Come back and I'll go over what I did to find the answers for those problems. All right. Okay, so I've written out all my solutions. Welcome back. Hopefully you gave that a try. And I'll go over what I did. So for example B, I had the natural log graph and I found the derivative. I set it equal to 0 and I tried to find out when it was undefined. So here's my derivative and I set it equal to 0 and I tried to find out when it's undefined. Set it equal to 0, I solved the algebra equation. I got x equals 0, so that's definitely a critical point. So x equals 0 is one of my critical points. And it turns out it's the only one because when I found out if 2x over 1 plus x squared is undefined, it can definitely be undefined because we can divide by 0 if we have the bottom of the fraction equaling 0. So if that bottom part's equal to 0, then it's undefined, and that would be another critical point. The bottom is 1 plus x squared, so I set 1 plus x squared equal to 0. But unfortunately, that has no solutions because that requires x squared equal 1, x squared equal -1, which has no real answers. So we get no additional critical points from the first derivative equaling undefined, but you do definitely have to check because sometimes you will definitely see that it's undefined and you'll have additional critical points. All right, then I took the second derivative. I had to use the quotient rule because I had a function on the top, function on the bottom. And I did a couple little simplifications. So this is what I ended up with after I combined stuff together. And then I set it equal to 0. And I also found out if it's undefined. Set it equal to 0 gave me 2 additional inflection points at +1 and -1. And turns out also this has a denominator, which could be equal to 0, but it also requires x squared equal -1. So it's not possible for there to be inflection points from when the second derivative is equal to 0. Okay, I'm not going to I didn't classify them this time, so I'll show you the non-classifying version. So I'm just going to do my increasing, decreasing by listing all of my critical points. There's only one of them, 0. So I listed 0, and then I put something to the left of 0, smaller than 0, and something to the right of 0, greater than 0. And I put those into Desmos, and I got the first derivative as a negative, that's decreasing. Then it's 0, that's the critical point. And then the first derivative is positive, that's increasing. So I know that all the way from -infinity to that critical point, 0, it's decreasing. And from 0 all the way off to infinity, it's increasing. I did the same thing with concave up, concave down. I have 2 inflection points, +1 and -1. So I listed them +1 and -1 here and here. But remember, because I didn't classify anything, I also have to stick my critical point in there. So there's my critical point. So not classifying means list all of the inflection points and critical points, and then do the number to the left, number to the right for each of these. So I have -2 to the left of -1, -0.5 to the right of -1. I'd use a decimal because 0 is another cutoff point. So it has to be between -1 and 0. So I just took a -0.5. I threw those all into Desmos, and I got negative numbers and positive numbers. I got negative for -2, 0 for our inflection point, positive, 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 all in this region, 0 for our next inflection point, and negative. So the negatives is where it's concave down, positives is where it's concave up, and the inflection points is where it switches. So I summed it up right here. From -infinity to -1, we get a concave down section. From -1 to 1, we get a concave up section. And from 1 to infinity, we get a concave down section. And we can look at the graph. This is what the graph looks like. You can see that it's sort of decreasing and then it's increasing. It kind of bows down. It has a downward on the left-hand side. It also has a downward on the right-hand side, but somewhere right here in the middle, it kind of bows upwards a little bit. I don't know if you can see that or not. Maybe I'll zoom in a little bit. Kind of see that classical parabola shape where it bows up. So that's where the section where it's concave up. A little harder to see when you're zoomed out a lot, but that's the information we found out using our calculus. Okay. And then for the second problem, I had this decimal thing. I took the first derivative, took the second derivative. I found it when the first derivative is equal to 0, when the first derivative is undefined. I found 3 critical points, 0, 3, and -3. And for the second derivative, I found 2 additional inflection points, one at square root 3 and one at negative square root 3. And this one, I did classify the critical points. So to classify critical points, we oftentimes use the second derivative. So this should say dy squared over x squared. So it is the second derivative is equal to 3x squared minus 9. So I took each of the critical point x values, 0, -3, and 3, and I plug them into the second derivative equation. And the first one was a negative second derivative. So second derivative being negative is concave down. That shape makes a maximum. The second critical point was 3 that I checked, and that gave 18, which is positive concavity, going up concavity. So that's a minimum. And likewise at -3, there was a minimum. So I know none of those are inflection points. They're only maxes and mins. So that means when I did my concave up, concave down calculations, I didn't have to include 0 or 3 or -3. Since I know none of those are inflection points, the graph cannot switch concave up, concave down unless at an inflection point. In some cases, a 0 or 3 or -3 could have been an inflection point, and I would have included them in my list of concave up, concave down. All right, so I'm going to classify things for increasing, decreasing. I had my 3 critical points, -3, 0, and +3. And then I just chose numbers to the left to right, and I throw them all into Desmos, and I got my derivative values, right? Increasing, decreasing is the first derivative. So you're going to plug all those x values into the first derivative. You're going to find out that it's decreasing over here and increasing over here, and the critical point in between. And now you can figure out, okay, so we have all the way up to -3 is decreasing, between -3 and the next critical point 0, it was increasing, etc. For concave up, concave down, I use the second derivative because second derivative tells me concavity. I only have 2 inflection points because I did classify all the other 3 critical points as not inflection points. So I have my 2 inflection points here and here, and you can see that the second derivative is 0 at those 2 locations, which of course is how we found them. And then I check to the left and to the right of each of these points. Choosing whatever value you want, I just chose -3 and +3 since I know those are to the left and to the right. I threw them into Desmos, and I got, for -3, I got 18 as the second derivative. So the second derivative is positive, so it's concave up. And the second number I threw in was 0. That was negative, so concave down, etc. And then I have my little summary right here. Increasing had 2 sections. So I look in the increase and decreasing list. I found out that from -3 to 0 was increasing, as well as from 3 to infinity. And the other sections is where it was decreasing. And concave up had 2 sections. There's a concave up section here and a concave up section here. And there's only one concave down section in the middle. And I wrote that there. Finally, we can just sort of verify that with the picture. So this all stuff right here, it has 2 increasing sections, one on the right and one sort of, between -3 and 0. It has 2 decreasing sections, one on the left and one sort of in the middle between 0 and 3. It has 2 concave up sections and one concave down section. So let's see what that graph looks like. Right here. Boom. All right, so let me zoom out a little bit. So that's the graph. It goes down decreasing, increasing, decreasing, increasing. This has a section right here, which is concave up because it has a U shape. There's a section in the middle, which is concave down because it has an upside down U shape. So that's can be confirmed. We can confirm all those intervals by checking out the graph. And of course, we know that there's no other places where it's increasing or decreasing, or switches increasing, decreasing. There's no other places where it switches concave up, concave down, because we did the math. We did the math, and we know the only possible places where it switches are these critical points and these inflection points. All right, so those are my solutions for all of the increase and decreasing concave up, concave down example problems. Hopefully that was useful for you. Maybe give us some practice and let me know if I can help out in any way. All right, well, hopefully enjoy your day. I'll see you in the next video.